Hello everyone, welcome you back to my channel and today's session is relates to introduction to computers part 2, that is number system. So let's get started now. So in the previous session we have discussed about what is a computer, application, characteristics of computers, evolutions of computer, generations of computer, what are the devices has been used in different generations like vacuum tube, transistors, integrated circuits, microprocessor, artificial intelligence. After that, we had discussed about the classification of computers. Then we discussed about the basic computer organizations. And in basic computer organization, it's been divided into different units like input unit, central processing unit, output unit. So we get to know about each and everything in our previous session. Now, introduction. So the topics for today's session is introduction to number system, types of number system, positional number system and its types, and we have different positional number system like decimal number system, binary number system, octal number system, hexadecimal number system. After that, we will see the conversions of number system, that how the conversion of decimal number system happens, how the conversion of binary number system happens, how the conversion of octal number system happens, as well as how the conversion of hexadecimal number system happens. Now, start it. So, as per the thing, first we have introduction to number system. Basically, what we can introduce in number system. What exactly is the number system? So basically a number is required for counting or to express the amount of some quantity. It consists of a group of symbols called digits, which are arranged in a definite manner. There can be many ways in which the digits can be arranged to form a number. This gives rise to what we call a number system. So in a simple language, we have to understand that number system is nothing but it's a collection of numbers. It can be any kind of number. Now, the number system has been designed in a different way. Like we have decimal number system, which has 10 digits, starting from number 0 ends with number 9. The octal number system has 8 digits, starting with number 0 ends with number 7. Then we have the hexadecimal number system, which has 16 digits, starting from number 0 to 9, and after that A to F. So as you can see, after the number 9, the letters, the English alphabetical letters has been mentioned over there, like A, B, C, D, E, F. So why it has been initiated? Because to um indicate the two-digit number, and as this is a hexadecimal means 16 digit. So end up with the 16 digit. The two-digit number get converted into a single digit. So number 10 is denoted as A, number 11 denoted as B, number 12 denoted as C, number 13 denoted as D, number 14 denoted as E, and number 15 denoted as F. After that, we have a binary number system which has only two digits, that is 0 and 1. Now, the number of digits in the system, in the number system, is known as radix or base. So, whatever the digits you see in a number system, we call it as a radix or a base. Thus, the decimal system may be called as radix 10 system, the binary system as radix 2 system. Now, the number systems are basically are of two types. One is called as non-positioning number system and another is called as positioning number system. So let's discuss further on this. So first we have non-positional number system. Using this system, the symbols, that is the symbol of I, it denotes to number 1. Symbol of double I denotes to number 2. Symbol of triple I denotes to number 3. And symbol of 4 times 4, that denotes number 4. And 5 times 5, the 5 times I denotes to 5, etc. are used. In non-positioning number system, each symbol represents the same value regardless of its position in the number. The symbols are simply added to find out the value of a particular number. The specified symbols which you have seen for the numbers, we could majorly denote it as a kind of a Roman number. Now, in positional number system, the positional number system uses only a few symbols. User uses few symbols called as digits. Let's take an example. The decimal number uh, 3977.39, and there is a symbolic to introduce uh, the decimal. We are in denoting the number 10 in a bracket, and how that particular decimal number is divided. So in that particular scenario, it's being divided as 3 multiplied 10 to the power 3 plus 9 multiplied 10 to the power 2 plus 7 multiplied 10 to the power 1 plus 7 multiplied 10 to the power 0 plus 3 multiplied 10 to the power minus 1 plus 9 multiplied 10 to the power minus 2. Now, what exactly is these? So 10 to the power 3 denotes to the thousandth position. 10 to the power 2 denotes to the hundredth position. 10 to the power 1 denotes to the 10th position. 10 to the power 0 denotes to unit position. And the number after the decimal, after the dot, denotes as uh, we have mentioned as 10 to the power minus 1. That means 1 by 10th position, and 10 to the power minus 2 denotes to 1 by 100th position. Now, the following four positional number systems are commonly used. Basically, when we talk about the positional number system, there are basically four types of positional number system we are commonly using. One is called as a decimal number system, one is called as binary number system, one is called as octal number system, and one is called as hexadecimal number system. Now, let's discuss few more things about those four positional number systems. First, we have decimal number system. In this number system, the base or radix is 10, and there are altogether 10 numbers, that is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And a number in a radix system would be written as a of n, a of n minus 1, a of n minus 2, till a of 0, a of 1, a of 2, till a of minus m. That is, sorry, a of 0, a of minus 1, a of minus 2, till a of minus m. In this representation, uh, an is called the most significant digit, that is MSD of the number, and a of minus m is called the least significant digit. Let's see the example. In decimal number system, 3967 of base 10 or 3967 consists the digits in which 7 is placed in the unit position, which can be written as 7 multiplied 10 to the power 0, 6 is placed in the 10th position, which can be written as 6 multiplied 10 to the power 1. 9 in the hundredths position, we can write it as 9 multiplied 10 to the power 2. And 3 in the thousandths position, we can write it as 3 multiplied 10 to the power 3. Now, when we see it, the particular way of formation, we can make the values written as 3 multiplied 10 to the power 3 plus 9 multiplied 10 to the power 2 plus 6 multiplied 10 to the power 1 plus 7 multiplied 10 to the power 0. When we make it calculated, we get the value as 3 multiplied 1000 plus 9 multiplied 100, 6 multiplied 10, and 7 multiplied 1. Now, there might be the question comes in your mind that as the as we have seen the specified values with 10 to the power 1, it came as 10, and 10 to the 10 to the power 2 comes as 100, and 10 to the power 3 comes as 1000. Why 10 to the power 0 is coming as 1? Because as per the rule of mathematics, whatever the number you have whose power denotes to 0 gives you the value of 1. That means after making the calculation, we get the value as 3000 plus 900 plus 60 plus 7. The answer comes as 3967. So the valuation of 3967 of base 10 is equal to 3967 only. We have binary number system. So the binary number system user only use two digits, that is zeros and ones. The base or radius of binary number system is 2 because it contains only two numbers. The particular uses, the circuits in the computer have to handle by two binary digits or bits rather than decimal number. This is one of the good valuation you can get to know. The short form of binary digits is known as bits. Then the computer only identifies signals in the form of digital pulses which represent either high or low voltage, and everything that can be alone with decimal number can also be done using binary numbers. Let's take an example. Convert the binary number to decimal numbers. So we have a binary number called as 100,111 base 2. So as per the number, we can see its position. So as we have 6-digit number, so the first number 1 is in the 6th position, then second number 0 is in the 5th position, for third number 0 is in 4th position, fourth number 1 is in 3rd position, fifth number 1 is in 2nd position, and sixth number 1 is in the 1st position. So how it's been calculated. So based upon that, it's been based upon the valuation of 2. So as we have six numbers, the six binary number, so based upon that, we start it from end, and the end value, the first position, is being calculated as the initial value, and initial is always denoted with the number 0. So we can mention it as 1 multiplied 2 to the power 5, 0 multiplied 2 to the power 4, 0 multiplied 2 to the power 3, 1 multiplied 2 to the power 2, 1 multiplied 2 to the power 1, and 1 multiplied 2 to the power 0. When we come out with the answer to these, so it comes as 1 multiplied 32 plus 0 multiplied 16 plus 0 multiplied 8 plus 1 multiplied 4 plus 1 multiplied 2 plus 1 multiplied 1. So the final answer to these series comes as 32 plus 0 plus 0 plus 4 plus 2 plus 1, which gives the answer as 39 of base 10. That means the binary number 1000111 base 2, the conversion value of decimal number to this binary number is 39 of base 10. Now, is here we can see one table, how it gets initiated. So we can see the specified decimal number starts with number 0, ends with number 9, and the binary equivalent to each decimal number is based upon this. Now we have octal number system. So as per octal number system, the number system with base or radix 8 is known as octal number system. There are only 8 digits, that is 0, 1, 2, 3, 4, 5, 6, 7. And each position in this number system represents a power of the base 8. The decimal equivalent of the octal number 3077 base 8 is 3 multiplied 8 to the power 3 plus 0 multiplied 8 to the power 2 plus 7 multiplied 8 to the power 1 plus 7 multiplied 2 to the power 0. The valuation comes after this series as 3 multiplied 512, that is the 8 cubes value, 0 multiplied plus 0 multiplied 64, 64 is the valuation of 8 square, plus 7 multiplied 8, 8 is the valuation of 8 to the power 1, plus 7 multiplied 1, 1 is the valuation of 2 to the power 0. Once we make the calculation of each and every number, we get the number as 1536 plus 0 plus 56 plus 7, and the answer comes as 1599 with base 10. So the valuation is 3077 base 8. The decimal value is 1599 base 10. So you can see the specified decimal as well as the octal with binary equivalent table in front of you. Now, as hexadecimal number system, the base 16 suggests choices of 16 single character digits or symbols. The first 10 digits are digits of decimal number system 0 to 9, and the remaining 6 digits are denoted by A to F, representing decimal value 10 to 15, where A is 10, B is 11, C is 12, D is 13, E is 14, and F is 16. The largest single digit is F or 15, one less that of the base, as I discussed in the start. Now, since the number 0 to 9 and alphabets A to F are used to represent the digits in hexadecimal number system, it is also called as alphanumeric number system. I already told you the valuation, the digit valuation which we see in hexadecimal uh, is known as the alphanumeric number system. Let's see an example. Convert the hexadecimal number 39A base 16 to decimal number. So 39A. So as we know, A is denoted as number 10. So let's make the calculation first. So as we have the 16 digits, so the calculation will be based upon 16 only. So as the number 39A base 16, so the series calculation will be 3 multiplied 16 to the power 2 plus 9 multiplied 16 to the power 1 plus A multiplied 16 to the power 0. When we make the calculation of this series, we get the result as 3 multiplied 256 plus 9 multiplied 16 plus A multiplied 1. Why 1? Because as I already told you, whatever the value you have, if it has a power as 0, the answer comes to as 1. Now, we make it reconverted, keeping the same valuation again. 3 multiplied 256 plus 9 multiplied 16 plus A. As A is representing the number 10, we change A to number 10 and we keep it as 10 multiplied 1. So after that, our calculation comes as 768 plus 144 plus 10, which gives the answer as 922 base 10. So the, the conversion value of 39A base 16 is equal to 922 base 10. Let's see. Here you can see the binary equivalent with the decimal and hexadecimal numbers. So as we have discussed the specified decimal number and its hexadecimal format, you can see the binary equivalent just in front of them. Now, next comes as the conversion of number system. I hope you are finding this PT informative. If you are finding this information informative for you and you have seen the video till now, please go ahead and hit the like button, share the video with your friends and family, and do subscribe the channel. Now, as we have seen the different formation of number system, now we will see the conversion of number system. That means how the specified number system get converted. So the first conversion comes as conversion of decimal number system. Then we have conversion of binary. Then we have conversion of octal. Then we have conversion of hexadecimal. So as for the conversion of decimal number system, so it happens like into the different form. Conversion of decimal number system, conversion to binary, conversion of octal, conversion of hexadecimal number. First we have conversion of decimal to binary. Let's take an example. Convert the 37.8125 base 10 decimal number to its binary equivalent. So I hope everyone has done LCM in their mathematics. So we have to use the similar formation. Like we have the number 37. So let's do the LCM of that. As we are converting it to the binary, so we will convert it with the help of number 2. Now, when we make the calculation in the multiplication table of 2, we cannot find the number 37. We get the number less than that, that is 36, and 36 comes as 2 multiplied 18 comes as 36. Now we have made the 36 as a result by multiplying 2 with 18, and we have left with number 1. So we will keep that number 1 aside. After that, uh, we are reducing 18 now. So we get 18 in the multiplication table of 2 with 2 multiplied 9, which comes as 18. That means we got the 0 valuation. There is no extra number left over here. So we keep the valuation as 0. Now we will deduct more. So in the multiplication table of 2, we will not find 9. So we have a lesser number of 9, that is 8, which comes as 2 multiplied 4 is equal to 8. Now, as we have discussed earlier as well, the same happens here. We have deducted 8 from value 9 and we left with value 1. Now we keep that 1 aside. Now we can see the number 4 also deducts by the number 2. That means it comes in the multiplication table of 2. That is 2 multiplied 2 is equal to 4. We do not have any number left, so we keep 0 aside. And in the multiplication table of 2, we can deduct 2 as well by 2 multiplied 1 is equal to 2. And we do not have any certain number left, so we use another 0 over here. Now, to represent the valuation of 37 base 10, we got the binary value now, but you can see the number has been mentioned from top to bottom. To initiate the valuation of binary, we use the number from bottom onwards to the top. That means the first number comes as 1, then 0, then 0, then 1, then 0, then 1. That means our total number comes as 100,101 base of 2. Now we have another number after the dot, that is 0.8125 of base 10. Now it will be get calculated in a different way. As we know that whatever the valuation is there, it's been initiated as a division format. So whatever the number we have after after the dot, so it's been initiated with a fraction format. Now to make it converted, we use the valuation in a multiplication format. Now you can see the fraction value 0.8125 multiplied 2, and it gives the valuation as 1.625, and the specified result is 0.625, and the number 1 which we see before the dot, we make it as a carry. Now in next fraction, 0.625 get multiplied into 2, which comes with the result as 1.25. Now the result comes as 0.25, and the one which was mentioned before the dot got carried out. After that, 0.25 get multiplied with 2, which comes with the answer as 0.50. And as we do not see any of the numeric number like numeric value 1, Before the dot we see only 0, so we keep that 0 as a carry forward to the next. Now, uh, 0.50 get multiplied with 2 and gives the answer as 1.0. That means as a result, we do not have anything left. It means 0.00. And that 1 which is there before the dot symbol will get carried forward. So the number get initiated as now. The thing is that whatever the numbers got carried forward, it will be calculated from top to bottom. That means the valuation comes as 1101. So the final valuation of 0.8125 base 10 is equal to 0.1101. Why 0 point? Because we are calculating the binary valuation of the numbers which is after the dot. Therefore, the final valuation of the decimal number which get converted to binary is 37.8125 base 10 is equal to 100101 dot 1101 base 2. Now, next comes as conversion of decimal to octal number. Now, it's one of the interesting parts. We have one example. Convert the 35.45 base 10 decimal number to its octal equivalent. So, the same way, the way we have done for conversion in binary, we will do the same in octal as well. But in binary, we have used the number 2. Here we will use number 8. Now we have the number as 35, which is mentioned before the dot. And when we multiply with the valuation in 8, we will not get the result as 35. We have a number below to that, and which get multiplied as 8 multiplied 4, which gives the answer as 32. Now from 35, 32 is gone. We have left with 3, number 3. So we kept that number aside. So therefore, 35 base 10 octal value is 43 of base 8. Now we have number after dot. So the fractional value comes as 0.45 into 8, which gives the answer as 3.6, and the result will be initiated as 0 0.6, and that 3 which is there before the dot get carried out from 0 0.6. We make it multiplied with 8 and comes with the answer as 4.8. The result will comes as 0 0.8, and the number 4 get carried out, which is mentioned before the dot. Now from 0 0.8 we will make the calculation. 0.8 multiplied 8, which gives the answer as 6.4, and we have the result as 0.4, and the 6 which is there before the dot get carried out again. After that, 0.4 multiplied 8 gives the answer as 3.2, and the result comes as 0.2, and we can carry out the number 3 from there. And after that, the the 0.2 get multiplied into 8 gives the answer as 1.6. The valuation comes as 0.6, and with a carry of 1, the 1 which is mentioned before the dot. So the valuation comes for 0.45 base 10 is equal to 0.34631 base 8. That means the final valuation of the number 35.45 base 10 is equal to 43.34631 base 8. Next we have conversion of decimal to hexadecimal number system. So conversion of decimal to hexadecimal number system. So we have one of the example for that. Convert the 22.64 base 10 decimal number to its hexadecimal equivalent. Well, the way we have seen the conversion for binary, we have used to conversion of octal, we have used 8. Now we are converting to hexadecimal format. That means we are using 16 now. So we have one number before the dot, that is 22. And in the table of in the multiplication table of 16, we do not have 22, but we have the value less than 22, that is 16. So uh, 16 is being multiplied as 16 multiplied 1, which gives the answer as 16, and we have left the valuation as 6. So the conversion value of 22 is being mentioned as 1 and 6. That means 22 base 10 gives the valuation as 16 of base 16. Now the valuation after the dot, that is 64, 6 and 4 get fractionized now. So 0.64 get multiplied with 16 and comes with the answer as 10.24. The final result is 0.24. So the number 10 get carried out from there. Now 0.24 get multiplied with number 16 and gives the value as 3.84, whose result is 0.84, and the number 3 which is there before the dot get carried out from here. After that 0.84 get multiplied with 16 comes with the valuation of 13.44, and the result is 0.44. The number 13 got carried out from the radix value. After that we have 0.44 multiplied 16 gives the valuation as 7.04, and the result comes as 0.04, and from the radix value the 7 get carried out. That means the final result comes for 0.64 base 10 is equal to A3B7 of base 16. Now there might be confusion comes that why A3B7. As I already discussed, I have shown you the specified chart, and I already told you the number starting from 10 to 15 has been denoted with the alphabetical digits, a digit showing from A to F. So A denotes to 10. So we have the number 10 over there, which get converted to A. Then we have number 3. Then we have number 13, which get converted to alphabet D. And we have number 7. So the final answer comes for 22.64 base 10 is equal to 16.A3D7 base 60. We have conversion of binary system. So now we have seen the conversion of the decimal system. Now we will see the conversion of binary system. Now the binary system get converted to decimal. We will do the binary to decimal conversion. Now we will do the binary to octal conversion. Then we will do the binary to hexadecimal conversion. So in first binary to decimal conversion, we have one example. as convert binary number 1101.101 base 2 to its decimal equivalent. As we can see, the valuation which is mentioned before the dot get to be in a positive series, and the numbers which are there after the dot comes to the negative series. So the valuation will be 1 multiplied 2 to the power 3 plus 1 multiplied 2 to the power 2 plus 0 multiplied 2 to the power 1 plus 1 multiplied 2 to the power 0 plus 1 multiplied 2 to the power minus 1 plus 1 multiplied 2 to the power minus 2 plus 1 multiplied 2 to the power minus 3. Now, these series get calculated and comes with the result as 8 plus 4 plus 0 plus 1 plus 0.5 plus 0 plus 0.125. And the final result comes as 13.625 base 10. We have binary to octal conversion. So we have one example, that is convert binary number 111111110100 base 2 to its octal equivalent. Now, to make it easy, we have to uh, group the specified numbers by 3. So first 3 1 will be written separate, after that 101, then after that 100. Now we have to specify the valuation of these numbers to its octal value. So as per the 3 digits, 111 denotes to 7, 101 denotes to 5, and 100 denotes to 4. Finally, the octal number is 754 base 8. Now, binary to hexadecimal conversion. Here we have one example. Convert binary number 11011000100111 base 2 to its hexadecimal equivalent. Now, in octal format, we have divided the numbers into the group of 4. Now, group of 3. Now we will divide the number into the group of 4. That means the numbers will be divided as 1101, 1000, 1001, 1011. And after that, we will specify the hexadecimal equivalent to those numbers. That is, 1101 is denoted as valuation of B. 1000 denotes to the valuation of 8. 1001 denotes to the valuation of 9. And 1011 denotes to the valuation of B. Therefore, the hexadecimal number is B89B of base 16. Now, we have conversion of octal number system. So, we in this conversion, we can make the conversion from octal to decimal, octal to binary, octal to hexadecimal. First of all, let's see about the octal to decimal conversion. We have one example here. Convert binary number 51.63 base 8 to its decimal equivalent. This can be written as 5 multiplied 8 to the power 1 plus 1 multiplied 8 to the power 0 plus 0.6 multiplied 8 to the power minus 1 plus 0.03 multiplied 8 to the power minus 2. It comes with the valuation as 40 plus 1 plus 0.075 plus 0.00046,875. So the final valuation is 41.07546,875 base 10. Octal to binary conversion. We have another example, that is convert octal number 51.63 base 8 to its binary equivalent. So, as per the number, we have expanded the valuation accordingly. 5 will be written as 101, 1 will be written as 001. After that, uh, after the dot, number 6 will be written as 110, number 3 will be written as 011. So the final valuation comes as 101,001 dot 110011 base 2. That means the octal number 5163 base 8 binary valuation is 101001 dot 110011 base 2. Therefore, the binary number is 101001 dot 110011 base 2. Octal to hexadecimal conversion. Here we have the example as convert octal number 345.30 base 8 to its hexadecimal equivalent. So, based upon this, we have like this, the octal valuation of 345.30, we convert it to the binary, and the binary valuation comes as 011 100 101 011 000. Now, for converging to the hexadecimal, we have to remember one point. For converting to hexadecimal is, if numbers are before period symbol, then the digits move forward to next digit accordingly, and numbers which are after period symbol, then the digits get borrowed from the next digit. Like here we see the specified number of 011 100 101 dot 011 000. So from the first number, the last two digits get moved forward and added to the second digit, and the first valuation 0 will be remains idle. So we convert that 0 with the valuation of 4 zeros and moving 1 1 to next and making it as 1110, and we have left with 0. So we move that 0 to next. Now there might be question comes to your mind that in the first number we have selected 2, and in next number we have selected only one number, because as per the concept, it's a concept of 0 1 2. That means 3 is with the valuation of power of 2. So the two digits from the binary number at the end will move forward to the next, and one digit uh, on binary will move forward, which is in the last, will move forward to the next. And as we have the unique value 0, so we are not moving anything from there. So that means it get converted as, the first valuation comes as 0000, second valuation comes as 1110, the third valuation comes as 0101. Now, after the dot, the valuation comes in such a way that the numbers get borrowed from the next digit. That means in the binary we have 0, 1, 1, and we borrow one digit from the next. That is, we borrow number 0 and it becomes 0, 1, 1, 0. And we do not have anything left over there and only zeros are left. So we keep the valuation as 0, 0, 0, 0, which converts to 0. Now, as per the hexadecimal format, 1110 represents to the value E and 0101 represents the value 5 and 0110 represents the value 6 and 0000 represents the value of 0. So the final answer comes as E5 dot 60 base 16. I hope you all are enjoying and getting the information regarding the topics which we are discussing till now. Let's move ahead, and if you are finding this slides informative and interesting, please go ahead and hit the like button. Do share the video and subscribe to the channel. Let's move ahead then. Next we have conversion of hexadecimal number systems. So hexadecimal to decimal conversion, hexadecimal to binary conversion, hexadecimal to octal conversion. Now, first of all, we will see hexadecimal to decimal conversion. So we have one example. It says convert the 5b.2e base 10 to its decimal equivalent. So the valuation is 5 multiplied 16 to the power 1 plus b multiplied 16 to the power 0 plus 2 multiplied 16 to the power minus 1 plus e multiplied 16 to the power minus 2, which comes with the result as 80 plus 11 plus 0.125 plus 0.546875. So the final valuation comes as 91.1796875 base 10. So the valuation is valuation for 5b2 base 16. I'm sorry, it's been mentioned as 10. Its base 16 is equal to 91.1796875 base 10. Now comes as hexadecimal to binary conversion. Now we have one example. Convert hexadecimal number 8b2f dot 9a base 16 to its binary equivalent. We can simply make the conversion because for hexadecimal format, when we converted it to the binary, we use 4-digit number, as this is a 16-digit valuation. So number 8 represents 1000. Number B denotes to 1011. Number 2 denotes to 0010. Number F denotes to 1111 dot. The number 9 denotes to 1001 and number 8 denotes to 1010. That means the final valuation of hexadecimal number 8b2f.9a base 16 is equal to 1000 1011 0010 1111 dot 100 11010 base 2, and this valuation is the binary number. Now we have hexadecimal to octal conversion. Now we have one example. Convert the hexadecimal number BDAF.AC9 base 16 to its octal equivalent. Now first of all, what we will do, we will convert the valuation to its binary format first. So B is representing 1011, D representing 1101, A representing 1010, F representing 1111, A representing 1010, C representing 1100, 9 representing 1001. Now, that particular binary formation, so that binary formation has been converted based upon the hexadecimal. Now we have to make it to the octal. So octal is initiated with the 3 digits. As we have seen earlier, each and everything has been carried forward in the things. So over here, the first number 1 will be kept separate. From there, 3 numbers will be distributed. That means we have left with 011. We'll keep it ahead. After that, we have 110. Then that 1 get carried forward to the next and kept it as 110. Then from there, 10 get to move ahead to next and make it as 101. And lastly, we have 111. So we keep it ahead. Now, after the uh, decimal, we change the value. We keep the value in a such manner. So valuation as 101. Then last 0 will move ahead with next and become 011. Then last 2 zeros will move ahead and makes 001. And lastly, we have 001. We keep it ahead. So after getting this binary octal values, we convert it to its actual octal valuations. So 1 denotes to number 1, 011 denotes to number 3, 110 denotes to number 6, 110 denotes to number 6 again, 101 denotes to 5, 111 denotes to number 7. After the decimal, after the dot, the number 101 denotes to number 5, 011 denotes to number 3, 001 denotes to number 1, and 001 denotes to number 1. So the final answer comes as 136657 dot 5311 base 8. So if you find this video informative, then please do like, share and subscribe the channel. And if you have any questions, then type the same in the channel comment box below to get the answer. Thank you and have a nice day and happy learning.